Let's take it away. So thank you again, everyone. So our second speaker for the day is Dr. Mark Mitchison in the Trinity College Dublin. And so he's going to talk to us about charging a quantum battery with feedback control. So take it away, Mark.
Okay, so thanks very much for the introduction. Thanks to the organizers for giving me the opportunity to talk about this. It's been a really nice conference so far. It's not easy to kind of encourage this level of discussion in the online format, so that's been really nice. So yeah, this is work that I've done with my boss John Gould in Trinity and with collaborator Javier Prior, who's now in Murcia. And so okay, I mean, for probably most of this talk, I'm going to try and just take it slow and explain what we're actually talking about and what we did. And then hopefully, because I think this kind of story of feedback control is maybe not familiar to everyone, even experts in open systems. So hopefully then once that's clear for everyone, then the results will be kind of intuitive and we can just go through them quickly at the end. Okay, so all right, so let me start with a kind of motivation. So we're interested in this kind of idea of a quantum battery, okay? So what is a quantum battery? It's simply put, it's a quantum system in which you store energy, okay? And I don't do this because I want to use it to charge my phone, okay? At least not yet. And maybe not ever, okay, but that's fine because they're interesting for many other reasons. So basically, a quantum battery is a sort of paradigm or a model for understanding energy transduction in a quantum regime. Okay, so the kind of questions that we might ask is sort of how quickly can I put energy into a quantum system? How long would it last there? How easily can I extract some useful work from the system? And how do sort of the quantum dynamical laws and how the kind of quantum how does quantum physics affect these processes, and how can it possibly benefit me? Okay, and part of the reason why this field has got so much interest, I think, in recent years is because indeed there have been sort of discoveries of genuine kind of quantum and many body effects, okay, that describe sort of battery charging, work extraction, and so on. Okay, so this is just a very non-exhaustive list. All of the references, I'm going to give you a disclaimer now, are non-exhaustive. I mean, it will be, I mean, there's dozens of papers going up now about batteries every year, and I'm not going to pretend to give an exhaustive kind of bibliography. So, okay, so that's basically the idea. We want to understand how we can change energy from one form to another in this kind of quantum context. I'm going to be looking mostly at the charging process. Okay, I'll explain in a bit more detail what that is later on. But first, let's just consider this general kind of problem or general setup, right? So let's think about what an ideal battery actually is. Okay, it's a system that we want to store energy in for a long time, and that means that it has to be well isolated from its environment. Okay, so that the energy doesn't just decay by dissipation. But a well isolated system is inaccessible. Okay, so we can't actually control it and put energy inside. Right. So the way that we typically kind of solve this problem is by having sort of two separate sets of degrees of freedom. So one, which is a very well isolated system that can store energy, and then another, which is like the charger or the contact, okay, which we can control, which we can drive, which we can put energy into, but necessarily, therefore, because it's controllable, it's also lossy. It's open to the outside world. Okay. And this dissipation is obviously going to limit the charging process. And that's essentially the problem that we're trying to solve in this talk. Okay, so there's various different strategies that you can use to try and deal with dissipation. Okay, one of them is just to try and live with it. But you see that basically, I'll show you sort of later on that basically this kind of does limit you quite a lot in terms of how much energy you can put in. You can try and use the dissipation and the noise as a kind of energy source, or you can try and suppress it by some control strategy. Okay, and our answer is going to be some kind of mixture of these things. So with feedback, essentially what we do is we measure some of the dissipation that's kind of coming off the system, and we use this to inform our control strategy moving forward. Okay. Okay, so this is a kind of general schematic of the setup of just a general feedback loop, really. Okay, so we have here basically this charger battery setup that I already explained. So we have our battery system here, and then we have some charger, which I'm going to model in a very simple way as just a qubit. Okay, the classic. And so this two-level system, you could think of it as an atom or some kind of superconducting qubit. This thing can be driven by, let's call it a laser, okay, some external drive, and it undergoes dissipation, okay? And we're going to collect some of this dissipation, detect it, and then basically feed it back into the drive in order to charge our battery. And so I just want to sort of mention that this kind of question of feedback in quantum thermodynamics has, of course, been studied by many people before us. More so in the context of kind of discrete feedback or kind of feedback with jumps. Okay, so I'm going to be considering the slightly different case where you have a Homodyne detection, so a kind of diffusive like measurement. Okay, and this is, in my opinion, quite a lot. I mean, it's quite non-trivial to understand the thermodynamics in this setting, and I think there's still open questions there. So, but okay, so before I get onto the dynamics, let me just first explain what do I actually mean by charging a battery. Okay, so hopefully this idea of ergotropy is familiar to many of you, but if it's not, I'll explain it now. So okay, so obviously charging a battery is related to energy. This energy depends on the state that the battery is in and the Hamiltonian. So here I'm thinking of the case where I've now sort of taken away the charger and I've just got my battery in the cupboard, okay, and I'm asking how much energy can I take out of this battery at some later time, okay? But you know that the battery charge isn't the same as the energy, right? Because I mean, in general, I could give you a block of metal in thermal equilibrium. This thing has a macroscopic amount of energy and a macroscopic number of electrons, but you can't use it to charge your phone, okay? What you need is something with some kind of non-equilibrium energy distribution that you can actually get something useful out of. And ergotropy is one way of quantifying that. So the ergotropy is basically the maximum energy, so the maximum work that you can extract from the battery by some unitary operation, okay? So you think about applying some unitary U to your battery state. This will lower the energy by some amount. And then you basically maximize this difference in energy over all unitaries. This gives you the ergotropy. And this was defined in this seminal work by Alaverdian and colleagues. And essentially you see that states with ergotropy are ones that are non-passive. Okay, and so passive states are essentially ones that either have population inversions or coherences in the energy eigenbasis. So this is a simple cartoon of the difference between a passive and a non-passive state. If I have some 3-level system, I have my levels ordered in sort of order of increasing energy, and these blobs basically represent the probabilities of being in these different states. So this state is passive because essentially the probabilities decrease with increasing energy. This state is non-passive because there's some population inversion. So by unitary operation, I can reduce the energy of this state and get some work. And so we showed in this paper last year how to basically isolate the 2 contributions to ergotropy, one which comes from population inversion and one from coherence. Of course, we were not the first people to realize that there's a coherent contribution, but I'm going to use this framework and these kind of definitions later on. Okay, so that's what I mean by charging the battery. So let me now actually explain how we do this sort of dynamically, okay? This is the setup, right? So let me first just talk about the battery and the charger. So the battery, I'm going to model in a very simple way as just a ladder of equidistant energy states, okay, which is described by this operator n, which just counts the number of excitations, okay, and there's d dimensions, so d levels of this battery. So you can think of the battery as like a qubit for d equals 2, or as a kind of a large spin. And then essentially the charger is a qubit, which I can drive and which undergoes dissipation. And this is coupled to the battery by just some simple kind of resonant interaction. So basically this allows energy to flow from the charger into the battery, okay? And then I'm going to drive my qubit with some drive where the intensity of the drive I can control, okay? So this drive is already written in the kind of, I'm going to use the standard approximations of quantum optics. This is already in a rotating frame under the rotating wave approximation, etc. Okay? So I'm assuming essentially that this bare energy scale is the largest scale of the problem, okay? All right, so let's break it down into steps. So first, let's think about what happens in the absence of any feedback. Okay, so I just drive and I have some constant drive. So we know then in that case, that basically, hopefully this is familiar to everyone in this workshop, that I have some kind of Lindblad master equation that describes the dynamics, where I have some Hamiltonian, and then I have some dissipative term where gamma is the spontaneous emission rate. Okay, so if I just look at the charging dynamics under this kind of assumption, then I see that it doesn't work very well, okay, because of the dissipation. And so what happens is if I plot the charge of the battery, so here I'm plotting everything in units of Emax, which is the energy of the highest level of the battery. So 1 is full charge, okay? So basically you see that the energy, which is the black line, kind of oscillates, but then it settles down to something like sort of 1/2 of the maximum. But the Algotropy is much less than this, okay? So this tells you that most of the energy that's going into this battery is kind of useless, right? And the reason for that is quite easy to understand if you think about the dynamics of the qubit on the Bloch sphere, okay? So I'm driving with sigma y, so that means I can basically think about everything in the xz plane of the Bloch sphere. So this drive, essentially what it does is it rotates my Bloch vector clockwise, okay? So it just sort of rotates me round and round. But then the spontaneous emission, okay, these basically when I emit a photon, then I get reset to the ground state at some random time, okay? And so when I take the ensemble average, I basically have a bunch of these rotating Bloch vectors with random phases, okay? Because the random spontaneous emission events basically randomize the phase. And this basically just creates some kind of essentially maximally mixed state or nearly mixed state in the qubit, which is not very good for pumping energy into the battery, okay? So we want to try and get beyond this. So let's now add another element. So let's think about what happens when we actually try and measure the spontaneous emission. Okay, and what we're going to do is we're going to think about a Homodyne measurement. Okay, so what a Homodyne measurement is basically you collect some or all of the photons that get emitted. Okay, and then you interfere them with a strong local oscillator which derives from the same source as the drive, okay? And what this basically does is it measures the phase of the field that's being emanated from the qubit, okay? So we're not now detecting the individual photons that get emitted, we're just measuring the phase of the light that gets scattered, okay? And this phase directly corresponds to the coherence of the qubit. So I get some measurement record sort of in my detector. This is a stochastic signal, okay, because of the fundamental measurement noise of quantum mechanics. So I have some white noise term, okay. But on average, this signal is basically proportional to sigma x, okay. And then this kind of feeds back into the system dynamics because I have some measurement back action, and this is described by this kind of super operator here. So I don't want to get too bogged down in the details, but I just want to emphasize that this leads to a kind of stochastic description of the density matrix. Okay, so we have this white noise that appears here. This is a fundamental feature of measurement in quantum mechanics. Okay, so I think it's easier to understand this dynamics by just looking at an example. So this basically shows an example of a trajectory that's generated from these equations. So this shows you what the measurement record actually looks like, okay? And this shows you what the expectation value of the kind of the qubit coherence is doing in time, okay? So this is a driven qubit, okay? So we're driving it, that means it wants to do Rabi oscillations, right? So you can see that starting to happen here, okay? But the measurement is also happening at the same time. And the measurement is trying to basically project the qubit onto either sort of plus or minus 1 value of sigma x, right? So it wants to localize the qubit on a definite sort of eigenstate of sigma x. So you can see that it starts to kind of develop some finite value of sigma x. Then the measurement starts to kind of produce some output telling the experimenter that, yes, we have sort of sigma x close to -1. And then essentially this measurement back action tends to localize the qubit on this side of the Bloch sphere, okay? And you see that if you look at the battery, this generates some kind of stochastic dynamics. But still not very useful for battery charging. Okay, so now the final ingredient is to try and introduce some feedback which uses this information that we get from the measurement. Okay, so how do we do this? Well, we do this in essentially the simplest way possible, which still turns out to be kind of complicated enough, I'd say. And so that's basically to make the drive proportional to the measurement record. Okay. So essentially, so just to remind you, this R is the measurement record. Okay, this omega is the Rabi frequency that we're driving. So basically what we do is we just essentially sort of feed the current that's coming out of this detector directly back into our kind of control device that modulates the intensity of the laser. So this is a linear relationship with sort of the measurement record. So this is the most general kind of linear thing I can write down. So I have some constant term, okay? I'm allowed to have some constant that doesn't depend on the measurement. And then I have some feedback term, which has an overall strength F, right? F is just a parameter. And then I have my measurement record, and I include also some delay time, okay? Because in general, my electronics have some finite time scale. I can't immediately respond to the measurement record. So that's all kind of encapsulated in this delay time here, okay? Then essentially following the kind of theory that was worked out in the 90s, and you can find lots of details on this in this very nice textbook, basically the dynamics of this state of the system is described by some kind of repeated application of this stochastic map. So in some small time step dt, we kind of describe the measurement evolution, which is given by this super operator M, which I showed you on the previous slide. And then given the measurement result, we basically feed back the result in some coherent operation on the system, okay? Okay, so I hope that that's relatively clear. I tried to kind of get everyone on the same page. So now, yes.
Can I ask a quick question? So does this measurement operator still have some stochasticity, or is that sort of averaged out here?
Sorry, yes, it does. Yeah, it does indeed. So this measurement operator is exactly this thing here, okay. And it has indeed the white noise, right? Okay. So I mean, I'm not going to get into the technical details, but in certain cases, it is possible to kind of average over the noise explicitly. Okay, mm-hmm. That's in the case basically where this feedback delay is negligible. So that's going to be actually the next thing that I'm going to show you the results for that case. But in general, to kind of, if you want to simulate this thing, you have to just simulate the full kind of stochastic evolution and average over trajectories. I mean, yeah. So the feedback itself is random, right? That's kind of a key element because it depends on this random measurement signal. So you're feeding back not only the kind of the average value that you want, but also this kind of random noise that you can't control.
Marty, go ahead.
Okay.
Yeah, so I have a kind of technical question.
Yes.
So here, if I understand correctly, in your master equation, basically you add up the dissipator and the presence of measurement device, no?
Mm-hmm.
So
yes, in this thing you mean?
Is this clear that it's allowed? Like,
actually. Right. So actually this is, I mean, I'm not adding together two different things. So actually it's not possible to have one of these things without the other. Okay.
Okay.
So it's a little bit, I realize it's a little bit counterintuitive, but so this actually connects, for those of you familiar with stochastic differential equations, this is an Ito equation, okay? And so but rather than getting into the technical details, basically, you can think about this almost like a kind of fluctuation dissipation type connection, okay? So basically, this gives you some fluctuating term, but there's also a deterministic drift term that's associated with it.
Okay, the dissipation then also comes from the fact that you are observing the...
Absolutely, yeah. So basically, that's kind of what I meant by we sort of have a combination of living with the dissipation, using it, and trying to suppress it. So we need the dissipation to get the measurement signal in the first place. So the measurement signal comes from monitoring the spontaneous emission. Okay.
Yeah, okay.
Now, in the case where the efficiency, so this is the detector efficiency, right? Nothing to do with thermodynamic efficiency, just to be clear. So when this detector efficiency is 1, then basically we really collect we kind of measure every single photon that gets emitted, okay? And in some sense, then we can use that information to kind of completely suppress dissipation. In the case where this eta is less than 1, then that essentially is the same as saying that some of the photons just fly away this way, okay? And we don't measure them, and some of them we do measure. And then you get really kind of dissipation in the way that you would normally think about, in addition to this kind of measurement effect.
Okay, thanks.
Okay. No, thanks for the question.
Mark,
please, yeah.
Another quick question, just on
yes.
this slide itself.
Yes.
Maybe I'm missing some very fundamental point. I'm thinking about the density matrix, but now you in the equation that you have an additional noise term for the density matrix. What does this really mean? I mean, I understand the physical picture you're trying to draw in terms of these measurements, But what does noise on a density matrix really mean physically?
Right. So it only makes sense if you put yourself in the shoes of the experimenter who has access to the measurement record. Okay. So what the noise basically means is you updating your description of the quantum system conditional on the measurement outcome. Okay. So if you, I mean, even in the absence, even if it's not a continuous measurement, right? You're kind of familiar with this idea, right? That basically, if you measure, just do a single discrete projective measurement on some quantum state, right? You know that your description is kind of stochastic because you don't know what outcome you're going to get, right? Once you know the outcome, then of course, basically you change your description of the state according to the outcome. But I mean, the actual description of that process is a random process, right? Because you don't know a priori what the outcome is going to be. And that's essentially what this random noise is telling you. I mean, it basically has some kind of random effect and some kind of deterministic effect. But I mean, even this random part is not completely random because of this super operator here. So this basically tends to kind of slowly project the qubit state onto some definite value of sigma x being plus or minus 1. Okay. But in this kind of random way, because essentially, I mean, so more physically, this kind of random term is really coming from the very large number of photons that are going into this detector, right? So in order to measure the phase, what you have to do is mix this beam with a very, very intense beam of light, okay? And then essentially you're counting a huge number of photons in any one kind of unit interval of time. And this in some sense almost erases, so the reason why you do this is because you don't want to detect the individual emissions, okay? Instead, what you want to do is detect the phase of this light. And you know that phase and amplitude are kind of conjugate, so you have to almost erase the amplitude information. So you have to have a very, very large number of photons. And this large number of detections will have some kind of fluctuations, and this is described to a good approximation by a kind of Langevin type noise. In the same way that Brownian motion, when we think about it as a kind of continuous process, really arises from a very large number of small kind of discrete collisions. Does it make sense what I'm saying? I don't know if I've gone down a bit of a rabbit hole here, but
yeah.
Well,
so
I need
Mark,
to think about this a little bit. Yeah, but please, sorry.
Right.
I think I will come back to you if I have further question.
Sure.
Yeah, Mark, can I just make a 10-second comment?
Yes.
Just to kind of, again, also to kind of just clarify this little thing, which
Yes.
is that if you think of cross operators, they go as m, rho, m dagger. And if you want to do measurements which happen at order dt, then you need the measurement operators essentially to go as order square root dt, so that you can, the quadratic m, rho, m dagger produces a thing in linear in time. And this is essentially the essence of Zeno effect, which is sitting there. So this is another way of kind of just seeing what is happening here.
Yeah.
And so, Mark, I just wanted to make that comment because I want to ask you about the Zeno effect, but I'll just wait for the rest of your talk.
Sure. Okay. Yeah, we'll come back to that at the end, I guess. I mean, I can already kind of anticipate the thing. So this is not really in the Zeno regime, and because essentially we assume the measurement is weak enough. But okay, but maybe we discuss it more at the end. But no, but thanks for the questions. I mean, I anticipated there to be some confusion about this because it's not so trivial to understand this. I mean, it took me a long time. So okay, so but maybe I continue. I hope that it's kind of clear enough for people. So okay, so we're going to do this feedback now. We're going to take our measurement signal and we're going to use it to kind of modulate the drive of our qubit. Okay, and so now the question is, how do we actually sort of design our control strategy? So what parameters to choose to actually charge the battery? Okay, so let's first think about the case where there's no delay. So essentially, whatever measurement outcome I get, I can just immediately make some change on the system in response. That's the ideal case. And so in that case, it's kind of nice because you can solve for the optimal feedback parameters analytically. Okay. And this is kind of already, I mean, this similar problem was solved already in 2001 for the case of a single qubit. And so basically, the optimal feedback is to have just no constant part of the drive and essentially just have some drive essentially with the opposite sign to the measurement record. Okay. And the reason why this works is kind of intuitive, right? So basically what you have is your measurement R, which essentially is proportional to sigma x. Okay, so let's say that the measurement starts to detect some finite value of positive value of sigma x. Okay, then you apply a drive with the negative sign, so that rotates you kind of counterclockwise in the Bloch sphere. Okay, but now then your measurement starts to pick up some negative value of sigma x, so then you apply a drive with a positive sign, and that rotates you clockwise. So you see that no matter where you are in the Bloch sphere, basically you get stabilized near the North Pole. Okay, so that's what this feedback basically does. All right, and this is only possible because the drive is actually kind of proportional to some observable of the state, right? And so when you stabilize near the North Pole, essentially you're creating this perfect source of population inversion. So when you couple it to the battery, basically you get perfect battery charging. And that's the case when you have completely efficient measurements. You see that if you kind of tune your drive to the right kind of value so that you balance perfectly the measurement and the kind of the drive strength, then all of the energy that you could possibly put into the battery gets stored as Algotropy. Okay, so you get this kind of perfect charging. But even if the efficiency is relatively low, okay, you still see that you actually get pretty good charging. So almost kind of 75–80% charge in the case of kind of 30% efficiency of your measurement. Okay, so that's quite surprisingly good. Another feature that I just want to kind of highlight is that when f is too small, then you don't do any charging in this way. Okay, and the reason is that basically when f is too small, then instead of stabilizing in the kind of the top hemisphere, you start stabilizing your qubit in the lower hemisphere, and then you no longer have any population inversion. And so even though you have some energy in the battery, the Algotropy is 0 because all of this energy is passive. Okay. All right, so that's the steady state that I showed you of the kind of ensemble average. But this kind of just gives you some idea of the dynamics, right? So this black line is essentially the ensemble averaged energy. The red line is the ensemble averaged Algotropy. But these kind of gray lines show you what the actual individual trajectories do under this measurement and feedback. And you see that actually they're pretty sort of, there's not very much dispersion, right? So even an individual trajectory quite closely follows the behavior of the average, right? And that's again a consequence of this kind of this feedback and the fact that you have essentially no time delay or no kind of meaningful time delay. And so, okay, I mean, because we've essentially assumed that our drive is proportional to the kind of dissipation and the measurement rate, then essentially the faster the dissipation, actually the faster that you charge. Okay. However, okay, so what about if we can't actually arrange for this condition to hold? Okay, so that might be the case if our spontaneous emission rate is very large, right? So then we might not be able to drive so quickly. So then if we can't get f to be larger than gamma over 2, then the best thing that we can do is a different strategy, okay, which is where we add some constant term to our drive. All right, and this basically stabilizes the state in the lower hemisphere, in the sort of the southern hemisphere of the Bloch sphere, with some finite value of coherence. And so the reason for this can again be kind of understood intuitively. So basically you have this constant drive, which just kind of continuously drives you clockwise. No matter where you are, you're always going clockwise because of this kind of omega 0. And then the feedback, which basically pushes you in a different direction depending on which side you are, okay? And so then hopefully you can see that essentially this will stabilize you in this side of the Bloch sphere, okay, in the lower hemisphere, which has some finite value of coherence. And this coherence gets transferred to the battery. And so you see that basically in the steady state, you do get some kind of advantage from this. You get some additional charge from the feedback. And this Algotropy that you get is purely coherent. So this blue line shows you what the kind of incoherent versus the total Algotropy is, and you see that the incoherent contribution from population inversions is essentially negligible. Okay, but this dashed and solid curves kind of compare the case with and without feedback. So you see that feedback it doesn't help. I mean, it only helps you a little bit basically. So the optimal thing to do is to really drive fast. Okay, and then this is just the final slide of results. So basically, so far I assumed that we really have this kind of perfect instantaneous feedback. Realistically, of course, we can't do things instantaneously. We have some finite delay and we have some kind of finite bandwidth. And so this we kind of represent by just delaying our feedback by some time tau. And essentially, the relevant comparison the relevant time scale for comparison is the kind of the time scale of the qubit dynamics, okay, which is basically set by this gamma, okay. And you see that if gamma times tau is relatively small, then essentially our feedback still works pretty well, okay. But you do get some additional kind of dispersion between different trajectories. There's much more kind of randomness being introduced, and this reduces the ergotropy, all right. But once this gamma tau starts to get really appreciable, then you see that very quickly the steady state kind of energy and ergotropy drops off to zero. And the reason for this is, again, intuitive, right? So basically, when gamma tau is large, so when the delay is large compared to the system dynamics timescale, then essentially by the time you kind of get around to applying your feedback, the system state has already changed to something completely different. Okay, so you might whatever you do is probably pushing it in the wrong direction, or it's the opposite thing from what you wanted to do. Okay. All right, so that's already everything I wanted to say. So basically, to summarize, we kind of considered this problem of using Homodyne mediated feedback to control the energy of a battery, which basically formulates kind of quantum battery charging as a feedback stabilization problem. And the intuition behind all of these results is that essentially we sort of, by choosing how we drive the charger, we can kind of turn it into an effective reservoir of ergotropy. And then when we couple our battery, this ergotropy just gets kind of transferred to the battery, and we can charge. So there's a lot of open questions in this field. I mean, I didn't even address really any kind of classic thermodynamics questions of efficiency, of entropy production. I think these things are quite difficult to formulate for this kind of feedback. I think this is still kind of an open problem for the community. But I'd be happy to discuss this in more detail with questions or whatever. So before I finish, just acknowledge my collaborators, so John and Javier. This is the archive version if you want to check out the paper. And let me also just advertise the poster of our RCHAC, another postdoc in Dublin, who's got a poster in the poster session. I think I'm probably the third talk now to advertise RCHAC's poster, so you know that it must be good. So please do go and check it out. And thanks for your attention.
Thank you very much, Mark. Prasanna, please.
Hi, thanks, Mark. This is a great talk. So one question I had is, now if I'm still trying to understand how feedback is different in some sense from a very clever sort of set of pulses that help me maintain my qubit in a particular state. For example, can I learn something from feedback and actually make a control protocol that would work as well? Learn from feedback, like theoretically, and then put the control from there. Is that a better strategy, or is there something more there from feedback?
Yeah, I mean, that's a really good question. So, I mean, probably it is the case that one could devise. So I'm not entirely sure, but probably it is the case that one can try and devise some kind of unconditional control scheme, right? Where if you understand the dynamics very well, and instead of using the measurement outcome, you just basically apply some kind of complicated time-dependent control. From looking into kind of other models, related models where this kind of thing was solved. So for example, if you have a qubit and a harmonic oscillator as your battery, so that you have some kind of James Cummings model, I mean, it is possible to engineer kind of arbitrary states of the battery, but you have to also control the coupling, right? So if you only control the Rabi frequency, I think this doesn't really work. Okay. Now, I don't know if this is really a fundamental thing, but this is just what I found from looking into the literature. So that's one thing. I mean, but it's a good, I certainly haven't proven that feedback is kind of better than this kind of control scheme you propose. So it may be the case that would work. But I think there's another interesting question that you asked, is like, what can you learn from the feedback? And this is kind of one of the open questions that I put in the end, which is that, I mean, in principle, you have a lot more. So everything that I plotted really is a kind of ensemble average quantity, right? This energy and this ergotropy, this is an ensemble average. So I'm imagining that I do this many times, okay? And then I take my big kind of ensemble of batteries and I try and extract work later on. But in principle, I actually know the individual states of each battery separately, because I've got the measurement record from each one of these protocols. And in that, given that information, I think you can probably extract more work than you would otherwise be able to. But this kind of takes you into this whole story of single shot thermodynamics, which, to be honest with you, I don't know well enough to use. But I mean, I think this is an interesting open question.
Thanks.
Okay, in the spirit of democracy, I've raised the hand myself. So, Mark, I just have one or two quick questions. I was going to actually bring up Zeno, which I think you've already answered. The other thing that I was going to bring up is the fact that there is an information record from the measurement record, and
Yes.
this harkens back to kind of the Maxwell's demon. Those classic set of problems that we've discussed through the community. And I think it'd be very interesting to basically see what, so two things I just want to say. One is that it'll be very interesting to see what the information, thermodynamic, trade-off is there, and whether this is something that can be discussed in a meaningful fashion. And the other is the other thing that I also want to bring up, which is again something that I'm sure you've thought of very well, which is that there are all of these schemes. John himself is involved in several of these, Juan Pablo Paz and others, where it's 2-point measurement to do basically energy extraction and all of the kind of subsequent tricks around it. So continuous measurement you can think of as essentially just just an infinite limit of that. And so to me, one of the kind of questions that I think comes up immediately is I can think of the measurement process itself as a work extracting process or a work depositing process, and which is exactly is sitting in your open questions. But I just wanted to also bring it up just for your reaction. What do you think of these two things?
Both very good questions. Okay, so let me first go back to the first one. The first question was really about this kind of incorporating the information from the measurement into this thermodynamic description, right? Yeah. And indeed, you should be able to do that. The difficulty that I had when thinking about this is how to actually connect this information theoretic quantity to something energetic that's kind of relevant. Okay, so the beauty of this kind of information thermo connection is that typically by looking at some kind of information theoretic quantity, like the kind of the correlations between your feedback controller and the system that's measured, you can actually get some bound on the energetics, right, on the work that you can extract. I mean, this is this famous Sagawa-Ueda result and the many other papers that followed. Now, I did look in particular in detail at the work of Sagawa to try and see if I could hijack this and use it for myself. But the difficulty that I came across is really the step of trying to connect the information that you get to the energetics, right? So the reason for this is basically because your system, okay, it's maybe not so clear from, okay, maybe it's clear from this plot, but the difficulty with this, and I think the obstruction to why this particular setting has been so difficult to formulate in quantum thermodynamics is because you have a set of trajectories through coherent states of the system. So instead of, I mean, with kind of jumps and discrete feedback, it's kind of relatively simple, because if you assume that your measurements are in the energy eigenbasis, then you always end up in some kind of classical state, in some energy eigenstate. But here the measurements are projecting you onto coherent superpositions of energy eigenstates. And this, for me, makes it very difficult to look at the energetics on a trajectory level, right? Because the individual trajectories do not have a well-defined energy. So I, to my knowledge, this has definitely been addressed by various people, by Alessandro Romito, by Alexei Ofev, etc. But to my mind, there's still not one like completely satisfactory answer to this. So I'd be very happy if people are interested in looking at this.
So last question from Junyan.
Yeah, sorry, maybe a very silly question. Can you explain the reason why you choose Homodyne measurement instead of some heterodyne measurement or some driven-dissipative measurement?
Right. Yes. Well, okay. I mean, I get, to be honest with you, I don't really distinguish that much between those. I mean, maybe I even should have not put Homodyne here, but rather just a general heterodyne. I mean, so essentially, I mean, okay, yeah, sorry. So I mean, okay, basically the point with heterodyne is you can kind of measure more than one quadrature simultaneously, right?
Yeah, so here this would be X and Y simultaneously, right? Yeah,
that's right. I mean, okay, this is actually a good question. So I'm not actually sure if we ever really considered this seriously, but I suspect that you probably don't gain that much more. I mean, essentially, so the reason that, I mean, let's say that the reason why sigma x is distinguished here, okay, is because the drive is in sigma y, right? So I mean, essentially, like you can only kind of significantly affect the quadrature that you're measuring, right? So it's true that you could do a heterodyne measurement and then measure some combination of sigma x and sigma y, but somehow in my mind, I still think that this would end up with some dynamics, I mean, effectively confined to a plane, but where this plane is just kind of changing in time, okay, as you measure sigma x and sigma y. Does that make sense? I mean, so basically, I mean, if you started to measure sigma y, then you start to basically move out of this xz plane, okay? So then your drive with the sigma y stops actually having an effect. So then you need to drive sigma x as well. But I think in the end, you probably get back to the same problem. But okay, I mean, I can't say this for sure, actually. This is a good point. So, but we didn't check this. But thanks for the question.
Thank you.
Okay, thank you, Mark, for this wonderful talk. So let's all thank Mark.